Okay, lecture 24, chemical reactions of alcohols. So we have a combustion reaction here, and all combustion reactions for these organic molecules have products of CO2 and water. So then it's just a matter of balancing. I'm going to balance them very quickly here. So 10, and then this should be, so that's, oh yeah, now here's the thing. So we have 8, 13. Now there's one oxygen over here, so that takes care of one of them, so we need to make this a 6 for 12. So 1 plus 12, 13, over here 8 plus 5. So don't forget about that oxygen. But the only tricky part, here we have 1, 2, 3, 4, 5 carbons. So it'll be 5 CO2s because all the carbons become CO2s. Then we'll have water. And the hydrogens, you don't see them all here, but I'm just going to put little lines to indicate as I'm drawing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now this is C. If there was no OH group here, this was just an alkene, that would be pentane, which would be C5H12. So all we do with an alcohol is put an oxygen between the carbon and the hydrogen. So we don't lose any carbons, we don't lose any hydrogens when we add an oxygen. So it should still be 12 hydrogens. So that's a nice little check there. So what did I say, 12? So this should be a 6 here. Then we have 10, 16 oxygens that we need. We already have one here. So we need to put a number in front of this oxygen to make it 15. Well, there's a 2 there already, so that would be 15 halves. We'd need to use a fraction here. And then we multiply through by 2 to get the end. If you don't like those fractions, it's always good. The only thing that will happen is like we can just put a number here and we're done, or a whole number, or we have to put a fraction, and the fraction is always going to be some number of halves. So if we needed 12 oxygen, so we just put a 6 here. We needed 15, so we had to put 15 halves. But you know, you can kind of, if you have to, you can kind of bounce back and forth until you count them up correctly. But shouldn't be too big of a deal. Okay, now this reaction, 180 degrees, and this is a secondary alcohol. Now the rules are that when you have a secondary or tertiary alcohol that at this high temperature with H2SO4, you're going to produce an alkene always. The only question is which one, which kind, because we have hydrogens here. Let me just draw them out, and hydrogens here. And the oxygen is either going to react with this hydrogen or with this one here, and so to produce water, and we'll get either a double bond here, or I'm just going to draw both possibilities, or here, plus water. Now, Zaitsev's rule, which we have to keep in mind, says that, let me read it off, the major product in an intramolecular alcohol dehydration is the alkene that has the greatest number of alkyl groups attached to the carbons of the double bond. Well, here are the carbons of the double bond for this one. There's 2 hydrogens and 2 alkyl groups. Here there's a hydrogen, but 2 alkyl groups. So since this double bond has 2 alkyl groups attached to it, this one does too, you can use either. No problem there. Now for this one, again, it's a primary alcohol, but it's a high temperature. So this is a primary alcohol, which means it's going to lead to an alkene. Only the primary alcohols can lead to the ethers, but only at low temperature. So really there's only one time you have to worry about that, and it should be fairly clear, as I'll show in a couple of reactions from now. So remember, this is where the carbon is with the OH group, and then there's hydrogens over here, and there's also a hydrogen here, but we're interested in what this OH group is going to do to this carbon. And you can see that it only has one choice. It has to go to this carbon because there's no carbon on the other side of it, so that's what makes it a primary alcohol. So I just tried to put it in the same form here, so that's going to be it, plus water. These are going to go off, and you're going to have an alkene. For this one, Now this one is where Zaitsev's rule has to be, we have to be careful about it. We have secondary alcohol, and we have, let me draw the two possibilities. We can, the OH group could go to this side, so we have a double bond here, or, since only one of these is going to apply, I'm going to put them below each other, and then, or here. Now, let me draw out the hydrogens on the alkyl group, so you can see, put a dot for the carbon. Oops. Now you can see that this alkene has one alkyl group and 3 hydrogens. This one has 2 alkyl groups, I should say, alkyl groups and 2 hydrogens. So this is the guy, plus water. And so most of the time it won't matter, but if you have an OH group that's near on the second carbon, then we're going to have to obey Zaitsev's rule. Here we have 2 primary alcohols and a lower temperature. So I give you 2 alcohols like this, and they're both primary, and it's a lower temperature. That tells you that you're going to be creating an ether. The H of one of the OH groups and the OH of another, and it doesn't matter which one you choose. If you want to take this OH from here and the hydrogen, or the OH from here and the hydrogen, you're going to end up with the same thing. Now what I do in this case is I take the, just so I can create the structure, is I write out this formula as O, and then I'm attaching this side. So we have this. Now it's just 1, 2, 3, 4. It's a dibutyl ether that we've created, and it looks kind of funny, but I just kept the same exact structure, and you can see that we just have an oxygen in the middle, and then we just attach the alkyl groups to either side. And that's all there is to it. Now make it a little more interesting. You could do it this way, where you just put the oxygen, and so we'll take this alkyl group and it'll go here, and then this alkyl group will go below. They're different, so we got to be careful. So we have this, boo, 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 like that. There, and there. So complex, but it doesn't matter what is here. All it's going to take is some extra work to make sure that you got the right group, or right alkyl group on each end here. Yep. Now, so that's only going to happen if they're primary. They're both primary alcohols, and it's at a low temperature. And I'm only going to use the temperatures they have in the book, 180 and 140. Now, you can have a higher than 180, and you can have lower than 140, but you know that these are the ones they choose. Those are the optimal temperatures for these kinds of reactions. So predict the alcohol from the following reactions. This is something from the book. So they don't tell you what you started with, and you have this reaction. Well, you know that it had been an alcohol, because that's what they say. So the OH group either went here or here, and so I'm just messing around with this. You know, I'm not changing it. I'm just showing where the OH groups could go. And in this case, it doesn't matter. It's perfectly symmetrical. So you can choose either one. And we don't have to worry about Zaitsev's rule at all. If we were near the end, if the double bond had been here, well, no, it wouldn't. If we had double bond here, that's the only time we'd have to decide between this side, the end, and here, and we would choose the primary. But yeah, in this case, we don't have to worry about it at all. Sorry, I'm just kind of thinking as I go here. So it's but in this case, there's no choice to be made. Now for this one, we have an ether, and I have alcohol just like they do in the book, but say alcohols here. In the book, the examples, each side of the ether was the same. These are different, and that's okay. So that'd be the one alcohol. We just write it like that. And then the other alcohol, so just tear it apart. We put them together before, now tear them apart. Next reaction. what we do in the case of an oxidizer, a strong oxidizer, that's what this means. KMNO4 is one of the is an oxidizer that's often used, but the oxidizer doesn't add it, or doesn't help us with the reaction as far as writing it out. It would just make it that much more complex. So that's why they usually leave it like that. And some of these oxidizers can be huge molecules. Since we're really only interested in what happens to the molecule here, then we don't write everything out. And let me just so even though we're going to lose a hydrogen along the way, we don't write where it goes because it becomes part of it reacts with the oxidizer. It's very complex. No need to worry about that. In organic chemistry, we do that a lot, where we focus on one reactant, one product, when there may be several reactants and products involved. So when you see an OH group and you see an oxidizer, change it to a double bond O, and then finish up with whatever is on the other side here. So we have two hydrogens. One goes off with the OH with the other hydrogen that's on here, and we're left with an aldehyde. So this is our aldehyde. For a primary alcohol, we create an aldehyde. A secondary alcohol, again, just do. And that does throw students as well. What about the rest of it? So they haven't told us what the oxidizer is, so we can't put it over here, and we can't balance the reaction. And it's because we're only interested in these in the main molecule. And this is going to happen in biochemistry quite a lot. We don't want to see everything that happened. Sometimes they do show us the full reaction, and it's quite complex. We just want to know what happened to that one molecule that we're interested in. The alcohol has then changed to a ketone when it's secondary. Now when it's tertiary, it's no reaction. Nothing happens. There's no place to put a double bond. There's already, to this carbon, it already has 4 bonds. And if we tried to make a double bond here, we'd have 5 bonds to that carbon. So tertiary alcohol, nothing happens. And that's it.